So let's recap now what we said. We said that this diagram shows the complete relationship between AI, machine learning, and deep learning. So at the center in green is deep learning. This is the most specialized and most recent technology. Deep learning uses multiple layers of neural networks to automatically learn representations from data. Surrounding that in orange is the machine learning category, where essentially we're saying that all deep learning is machine learning. But of course, not all machine learning is deep learning. So machine learning will include simpler techniques like linear regression, decision trees, support vector machines, and many others. Finally, we have artificial intelligence in blue. This is the broadest concepts. All machine learning is AI, but AI includes other things like rule-based systems, expert systems, and other approaches that don't necessarily involve learning from data. So this helps you understand why these are not competing approaches. They're nested categories. Deep learning is the most powerful and most recent, but it's not always needed. So sometimes a simpler machine learning approach is more appropriate, more interpretable, and more efficient. Okay, so we don't always use deep learning unless really we have to deal with features that are not obvious, or we have to deal with unstructured data. So now let's talk about the foundation of deep learning, the neural network. So a neural network is structured like the human brain and consists of artificial neurons, also known as nodes. And these nodes are stacked next to each other in three types of layers. So we have the input layer. So every network will have an input layer which receives the raw data. Each node in the input layer represents one feature or a variable. If you're analyzing an image, for example, that is with resolution 16 by 16 pixels, this means that you will have 256 input node 1 for the intensity of each one of the pixels in that image. The hidden layers come after that, and these are where actual computation actually takes place. So these layers don't directly receive input or produce output. They're in the middle processing the information. Okay, so deep learning networks will have multiple hidden layers, which is where the deep in deep learning comes from. Each hidden layer applies mathematical transformers to extract patterns and features. And finally, you have the output layer. This produces the final prediction or classification. If you're classifying whether an email is spam or not spam, you would have one or two output nodes. If you're classifying handwritten digits between 0 and 9, for example, you would have 10 output nodes, one for each possible digit. So this chart right here shows us the information flow through the network. So each input node will connect, each input will connect to an input node, as you can see here. And then each input also, after that, will connect to nodes in the hidden layer through weighted functions. Weighted connections right here with different weights, W1 all the way to Wn. And then finally, the hidden layer connects to the output. Each hidden layer then applies mathematical transformations to extract patterns and features. And finally, like we said, the hidden layer connects to the output, as you can see here. So the key innovation is that the network learns what weights to use. So during training, the network will adjust the weights inside the hidden layer and the input layer to make sure that its prediction is as correct as possible over as many examples as possible. So over time, it learns the right weights to make accurate predictions. Let's look at a concrete example that makes all this more real. Handwritten digit recognition. So imagine you want to build a system that can read handwritten digits. So recognizing whether someone wrote a 0 or a 1 or a 2 or a 3 and so on. So this is a classical problem in machine learning. So the input is an image of a handwritten digit. And in the example you see here, this image is of resolution 16 pixel by 16 pixel. So we have a total of 256 pixel, where each pixel is a binary number. So we're not really tracking the intensity here. We're just tracking whether the pixel has ink in it or doesn't have ink. So a 1 would represent that the pixel is full of ink. A 0 would say that the pixel has no ink. So this will give us a total of 256 input values. These 256 values then become our input layer to our neural network, and the 256 nodes, each representing 1 pixel intensity. So that here's intensity is not a continuous number, it's just a 0 or a 1. Now the information will flow through the hidden layers, and these layers learn increasingly sophisticated representations of what makes a 2 look like a 2. So the first hidden layer might learn to detect edges, and then the second layer will maybe learn to detect curves and corners, and then deeper layers will combine these into higher level concepts. Finally, the output layer will have 10 nodes, and then one for each digit, obviously, and each node will represent the network's confidence that the input digit is that number. So for example, here the output, you can see that there's maybe a 0.1 probability that it's a 0 or a 1, and a 0.7 probability that the number is a 2, and then so on, and then 0.2 probability that it's a 0. So we conclude that the highest probability is that this number is a 2. So the interesting thing is that the network learned to do this classification by seeing thousands of examples of handwritten digits during training. No human told it what features to look for. It discovers that pixel patterns in certain locations are important for distinguishing digits. So it learns the features automatically. So this is the power of neural networks and deep learning. Whether applied to handwriting recognition, image classification, natural language processing, or risk management, in finance, the principle is the same. You feed the network raw data and correct answers, and then it learns to extract the patterns that matters. Now, if we extend our handwritten digit example to really understand what's going on in the neural network. When a handwritten digit enters the system as a 16 by 16 pixel image, so as we said, we have 256 input values. But here's the important part. The network is not just memorizing when the pixels are arranged this way, it's a 2. remember that different people will write it two different ways. Instead, it learns abstract representations. So in this diagram, we can see that the network takes the 256 input pixels and produces a 10 component vectors, one for each possible digit from 0 to 9, which represent probabilities, as we said. But the real magic happens in the hidden layers between the input and the output. Those hidden layers transform the raw pixel data into increasingly meaningful representations. So mathematically, our machine here is a function that takes a 256 pixel representation and reduces it to a 10 vector in R10. So we're mapping from the 256 dimension input space to 10 dimension output space. The neural network then represents a function that does this mapping. So this example illustrates a fundamental principle, is that neural networks learn to extract the right level of abstractions for the task at hand. They don't need a human to say, look at the curved parts or look at the horizontal lines. The network will figure out by itself what matters through training on many examples.